Lesson 2 is on the scientific method, and you have a lecture with this lesson. Remember, you should have already read the textbook reading that was corresponding to this lesson, and you should have completed all your definitions. And now it's time to do your lecture. So you should have a notebook that you're taking your notes in, and a piece of paper, pencil, pen, everything that you need to take good notes. Remember, this is not a TV show. You're not just sitting back watching what's happening. You're actively involved, taking notes, pausing the CD as you need to, turning it back on to continue the lecture, and rewinding to go back over a certain concept until you understand it. Well, let's start this lecture by defining what the scientific method is. And here's a definition out of Webster's Dictionary: the systematic collection and classification of data, and usually the formulation and testing of hypotheses based on the data. So let's just look at a couple of the words here. Systematic, what that means is just a step-by-step approach, or an organized approach. So if you have a systematic collection of data, you have an organized collection of data. Data, that has to do with the information that you record when you do an experiment. Whether that's some certain numerical values or quantities or weather conditions, data is the information you record during an experiment. So the scientific method, that's a systematic or step-by-step approach, and in that approach you collect data, and then you also formulate and test hypotheses. We'll talk about what a hypothesis is in a minute. And another way to think about the scientific method, this one might be a little bit easier to understand: a step-by-step method used to answer a question. That's another easier way of thinking about the scientific method. A step-by-step method used to answer a question. And remember, in Lesson 1 we talked about what inductive reasoning was: a step-by-step method that follows the inductive reasoning process. In other words, we start with facts, things that are observed, and we draw general conclusions based on those facts. So if the scientific method is a step-by-step method, it must have different parts to it. And so let's talk about some of those parts first. Here are the main parts, and this is the order that they go in: question, hypothesis, methods, results, and discussion. And you always start, anytime you're going to do the scientific method process, you start with a question. When I was working on my PhD, I think the best thing my PhD advisor told me was he just kept drilling into my head to think of questions. He would just say, well, what's your question that deals with what you're talking about? Developing good questions, that's the beginning of having a good science experiment and following the scientific method. You have to start with a good question. And also look what I have written there. This question, it must be able to be answered by making observations, by seeing, tasting, touching, smelling, hearing, using those kinds of observations. Sometimes there's things that you can't see, like the wind. You can't see the wind, but you can see the effects of the wind. You can feel the wind. You know it's there. And if you have some method of collecting information about that wind, then that's something that you can use, and you could do a science experiment on the wind. As long as you have some way to make observations. That's how a good science experiment starts, is with a question that can be answered by making observations. Now, I've been using the word science experiment a lot here. That's what you do when you do the scientific method. You're applying the scientific method to an experiment. So you start with a question, and then you come up with a hypothesis or an educated guess to what you think the answer to that question might be. Now look at what a hypothesis is. It's an educated guess. It's not a blind guess. So you have to become educated. That means you need to do a lot of reading and then talk to people who may know something about your question, and that will help you make a good, educated guess to what you think the answer to your question is. And when you're doing your research, when you're doing your reading, when you're talking to people that may know something about your question, keep a journal, like a big notebook of some kind, and record every book, every website, every person that you use in developing your hypothesis. For example, maybe you had a question that was, what brand of dog food will make puppies grow the fastest? Well, to figure out what the answer to that question was, you wouldn't just go and buy one brand and try it. You would buy several brands. You would go and do some research. You would see what different manufacturers claim that their dog foods will do for puppies and for making them grow. And you'd probably talk to some people who are experts in the field. You'd talk to some veterinarians and ask them what kind of dog food they think will make a puppy grow the fastest. And you might get on the internet and do a search on foods for puppies and see what you find out there as well. And so you'd have all of this information and you would use it together to help you make a good hypothesis, a good educated guess to the answer for your question. In order to stay organized, you would record all the information that you collected in one place in a journal. So we've talked about our question. That's always how we start doing a science experiment following the scientific method. Then we have a hypothesis, and then next is actually performing the experiment. That's called the methods section. Question, hypothesis, then your methods. And that consists of two parts within the methods, the materials and the procedure. The materials, that's just all the materials that you'll need in order to conduct your experiment. And so you just start thinking about, how am I going to answer this question by doing an experiment? What materials will I need? And you exclude any materials that won't help you answer your question. You only use materials that will help you in answering your question. And then your procedure, that's where you'll write down how to perform your experiment. Like if you were cooking something, you'd have a recipe to cook that particular product, like cookies or something. You'd have a recipe that you were following, a step-by-step method on how to bake those cookies. In the same way, in the scientific method, the procedure, you have a step-by-step method on how you will perform your experiment. I've underlined what the most important part to remember about the procedure is. You want to write your procedure so that someone else could repeat and to verify your experiment. Verify just means to prove whether you did it correctly or whether they get the same results that you did. Again, you can record this procedure in the journal, and the procedure will change. You might practice your experiment once or twice before you actually do the real thing, and your procedure will change as you get better and understand how the best method is to answer your question. Eventually, you'll come up with a good procedure that you could give to somebody else. You'd say, here's my materials, I've got those listed, here's the procedure. See if you can verify my experiment based on this information. So you have your question, you developed your hypothesis, now you have your methods. The next part is the results, and that's your data. And you'll record this data in your journal, and you record all the data that you collect during your experiment. And in your journal you may want a section that you title raw data, and that's just all of your information. Later on, you'll organize this raw data into tables or graphs. You might average some information. If you have numerical values, you might want to average those. But most always, you put all of your data into a table or a graph form, and that's an easier way of presenting it to the public. In your journal, it can be a little bit messy sometimes. I mean, you want to try to stay organized in your journal, but you can get a little messy and disorganized in there to some extent. But in your final results, when you're trying to explain them to somebody else, you want those to be neat and organized, and that means you want them in the form of a table or some kind of graph. And again, everything has to tie back to answering your question. You only want to show results that will answer your question. You want your results, you want somebody to be able to look at those and say, oh yes, their hypothesis is correct, or no, it's not. I can tell that based on those results. For example, maybe you were doing an experiment on what kind of dog food made puppies grow the fastest, and you had 100 golden labs. And let's say you had 4 different types of dog food, and you broke the 100 labs into 4 groups of 25. You weighed them all initially, then you fed them all for, let's say, 2 months, and then you weighed them all again, and you looked at the difference in their weight gains. Now, you wouldn't want to show somebody 100 results. You'd want to have your 4 types of dog food, and you would average the weights for each one, and you can make like a table or maybe a bar graph to show your weights, and then somebody could look at those results really easily just at the averages, which would just be 4 numbers instead of 100 numbers, and it would be a whole lot easier to see whether your hypothesis was correct, and they could see, oh well, this brand had the biggest change in weight, so that must be the best type of food to use. So you want somebody to be able to look at your results and quickly see if the answer to your question was yes or no. And then that leads us to the last part of the scientific method. We have our question, hypothesis, methods, results, and the discussion is the last part. And its name speaks for itself. This is where you discuss whether your hypothesis was correct or not. And you also say why. In our dog food example here, maybe we had brands A, B, C, and D. And your hypothesis was brand C was the best, or would make the dogs grow the fastest. But in your experiment, brand B worked the best. So you would say that your hypothesis was incorrect. And that's okay. That's a part of science. You're learning something new. A good question is something that nobody's asked before, a question that nobody's really asked before. And so you're not really sure what the answer might be. And I know a lot of times you want to always have the right answer. And so you think, well, I'm doing this test and I've got to have all these answers. They're either right or they're wrong. That's one thing that's different when you do the scientific method, because you're asking a question that nobody knows for sure what the answer is. So if your hypothesis is incorrect, that's not necessarily a bad thing. Now, if you were lazy and sloppy in doing your research, that's one thing. But if you did everything in a neat, organized way and your hypothesis was incorrect, and then also maybe you let somebody else repeat your experiment and they verify it and they also show that your hypothesis was incorrect, then that's okay. Performing the scientific method is one place where it's okay to be wrong. And that leads to further investigation sometimes. And that's one part of your discussion that you want to do, is discuss further questions that may be asked that relate to your topic. Also, you want to discuss sources of error in your results. Why maybe did the results come out the way they did? What are some sources of error? And you never want to say, well, human error is a source of error. All error is ultimately the result of humans. Even the instruments that you use were built by humans, so they are subject to human error as well. So you want to be specific when you're talking about the types of error that you may have. It may have been you recorded the data wrong, the batteries were dying in your instrument, so that might have affected your results, different things like that. But you do want to discuss how the error that's inherently involved in any experiment, how that may have affected your results. Another good idea is to discuss some of the practical applications for your research. In our dog food example, those results might help you to figure out what brand is the best, or what types of food that brand is made with, which ones help the dog grow the best. That might be another question that you might want to ask based on your research. Or it just may help you with a decision on buying dog food. Now, if you did an experiment and your hypothesis was correct, you still need to explain why you think it was correct. You're saying, well, this table shows me that it's correct. These results show me that it's correct. If your hypothesis was correct, that shouldn't be the end of your experiment, though. You want to verify it and show if it's really a valid result or not. And remember, we talked about verifying already. Verification means that somebody else repeats your experiment, or maybe more than one group repeats your experiment, and they see if they get the same results. That's why it's so important to have those methods written so that someone else could repeat your experiment. Now, we've talked about the results of scientific experiments. In Lesson 1, we talked about how science gets close to truth, but it's never 100% true. Now, if several people verified your experiment, that idea that develops from that type of experiment, that might be called a theory. For example, in our dog food experiment, if 10 or 15 or 20 people repeated your experiment with the same results, there might be a theory developed that this certain brand of dog food is the best brand. Then if several more people, maybe for 10 or 15 or 20 years, just hundreds and thousands of people repeat this experiment with the same results, then that experiment may be elevated to a law, a scientific law. So in the field of science, you start with a hypothesis. That's the most basic form of an idea. If that's proven several times with the same results, then it becomes a theory. And then if that's proven even more and more, that becomes a scientific law. And there's no set number of times that an experiment is done and repeated to become a theory. And there's no set number of times that it's repeated and verified for it in order for it to become a law. A lot of that is just subject to human discernment or human understanding of what's going on. And also sometimes it's based on bias in the scientific community. Sometimes it's difficult to get people to change their way of thinking. And even though it seems strange, people will continue to do the same thing over and over, even though new results show that that way is wrong and that way should not be accepted. So ultimately, though, if you're dealing with a hypothesis, a theory, or a law, it's just important to remember that the results of scientific experiments are never 100% true. Now, let's go on and let's talk about writing a scientific paper. We've talked about the scientific method, we've talked about the 5 parts, and you can see how there's a lot of different things you need to write down. You need to write down a question, a hypothesis, write down your methods, write down your results, and record those in a table or a graph, and then write down your discussion. Now, when you're writing a scientific paper, or you might call it a science report, some people call it that, something to think about is usually what you do is put the question and the hypothesis, you group those together in a section titled the introduction. And in the introduction, you should introduce your topic. Make a smooth transition into your question and hypothesis. For example, in your dog food experiment that we've been talking about, you might introduce the topic by talking about breeding dogs or raising dogs, and then talk about some of the claims that some of the different brands make about their foods, and then you would lead into your question and then into your hypothesis. And when you write down your hypothesis, remember the definition of a hypothesis is an educated guess. So you have to write down where you got educated, and those are called your references. Somewhere in your scientific paper you must include your references, the information, the books, the people, the websites that you use to develop your hypothesis. Sometimes you put them in a separate section at the end of your paper and you title that section references, or you can put them in parentheses after each place that you use them. So your introduction, you lead into your question and then into your hypothesis. Then all the other sections, they should be separated by subtitles. For example, you should have the title to your paper, whatever the name of it is. Then you would have a subtitle that you usually center in the middle of the page. You'd title that the introduction, then you'd write your introduction, then you'd have your methods section next, then you'd have your results, and then your discussion. The whole time you're doing your scientific paper, you should try to remember that the purpose is to answer this question. So everything that you write should tie back to answering your question. You should be thinking, is what I'm writing right now, is that going to help me answer this question? Will it help someone else who wants to repeat this experiment answer the question? And your scientific paper, it doesn't have to be long. It has to answer the question clearly and effectively. That's the most important thing. A lot of times students think, oh well, if my paper is this long, then that makes it good. But that's not the case in a scientific paper. The most important thing is that it answers your question clearly and effectively. If it takes one page to do that, which it probably will take more than that, but if it takes one page, then that's fine. If it takes 10 pages, then it takes 10 pages. Now, writing a scientific paper, that's one way of presenting the experiment to the public. You can give your scientific paper to different people and tell them about your experiment that way. Another way is to participate in a science fair. And for most science fairs, you'll make a project board like the one in this picture here, and that project board and that poster should follow the scientific method. The poster would include all the different parts of the scientific method. It would include all the parts that you put in your scientific paper. And some things to think about: if you do participate in a science fair, you'll be competing against other people. So you want your board to stand out, to be different from other boards. And you can make it colorful. Add pictures of yourself doing your experiment. And also at a science fair, you'll be doing a lot of talking. You'll be explaining to judges how you did your experiment and what your results were. And so you want to have your board set up so that you can quickly and clearly explain your question to them, explain your experiment, and show them your results so that they can make a decision themselves if your hypothesis was correct or not. And for example, on this project board, you can see the results were displayed clearly in table form and in the form of a pie graph. And that's important because a judge could come by and they could see really quickly and really easily, and you could point to it really easily, point to your results and show them the results of your experiment and help them understand if your hypothesis was correct or not. And then you should also have your journal present as well. And that way the judges can look through that and they can look at your detailed information if they want to see a little bit more detailed information about your experiment. I encourage everyone in high school to participate in at least one science fair. I think it's a really good idea for you to do, especially if you're thinking about going into a science or engineering related field once you graduate. A science fair, it looks good on your high school transcript, and it just gives you a chance to express yourself and express your ideas. Well, that's all for the lecture for Lesson 2. Well, there'll be a pause here, and then the review question solutions will begin. Remember, now you need to pause the CD, go ahead and complete your review questions, complete every single one of them, then turn the CD back on and check your solutions. I consider it cheating if you continue on right now and look at the review question solutions, then go back and do your review questions. Question 1 was designed to make you think about how to answer a question doing the scientific method, and the question was, what brand of fertilizer makes roses grow the fastest? Now remember, you're supposed to have your review questions printed out so that you can be reading and watching the CD solutions at the same time. The first part, question A, was how would you come up with a hypothesis for your question? And what you could say is you could read the brands, read about what the brands claim. You could ask a nursery that carries all 3 brands. Those are just 2 ways that you could come up with a hypothesis for your question. So to come up with a hypothesis, that means what kind of research will you do to figure out what your hypothesis is, or to figure out what an educated guess is to answer your question. Now there's more than just these 2 ways here. You could also look at websites, read books, things like that. As long as you have at least 2 different ideas on how to come up with a hypothesis for your question, you should get the full 2-point credit for that particular problem. Now the next question was, how many different groups of roses will you have? 3 or 4? Well, you'll have 4. There'll be 3 treatments, brand A, brand B, and C of fertilizer, and then you'll have a control. Remember, the control is the one that you don't apply any fertilizer to. So you would have 4 different groups of roses, or 4 treatments. Then question C, would it be better to use 5 or 50 rose plants in each group? Well, it would be better to use 50 plants. And the reason for that is the more that you use, the less chance there is that one outlier will significantly affect the results. If you just had 5 roses and maybe one of them died, that would be considered an outlier. Or maybe one of them just grew like 5 times as fast as the other ones. That would mess up your average a lot more than if you had 50. If you had 50 roses and one died, you still have 49 roses to get your average results from. So in doing a science experiment, it's always better to have more data than less data. Sometimes this depends on how much time you have and also how much money you have to spend, because sometimes repeating an experiment, like in this case you'd have to buy 50 rose plants, that could be kind of expensive. It would be cheaper to buy 5 rose plants, but you would just have to know that your results wouldn't be as believable. Now the fourth question was, what measurement would answer your question better? The final height of plants or rate of growth? Well, just think about the question. What brand of fertilizer makes roses grow the fastest? So would a measurement of the final height of the plants or would a measurement of the rate of growth be a better measurement? Well, I think the rate of growth would be better because the question used the word fastest, and fastest, that has to do with a speed or a rate. So when the measurement to use in your results would be a rate, measuring the rate of growth, the change in growth over the change in time. Question E says, if you were at a science fair and you needed to display your results on a project board, would it be better to average your results for each treatment and make a bar graph, or list all of your raw data in a table? Well, let's just think about this. You have 4 different treatments, and let's say you used 50 plants in each group. That would be 200 plants. So that wouldn't be a really good idea to just list all of your raw data in a table. It would be better to average each group, and then you would just have 4 numbers to deal with instead of 200. And that's a lot easier to understand. It's a lot easier for a judge, if they're walking by, to just look at 4 numbers instead of looking at 200 numbers. It would be a lot easier for them to draw a conclusion about your experiment, and it would be a lot easier for you to explain whether your hypothesis was correct if you had a bar graph with just averages of your results. Now part F, if your hypothesis was proven correct by the experiment, what would be the best next step? Would you buy the fertilizer brand for your roses, or would you verify your experiment? Well, it's always better to verify an experiment. That may not be what you would do, but it would be the best thing to do, would be to verify. I mean, you don't have to. You could go ahead and go buy that fertilizer brand, and then if it didn't work, it didn't work. But the best thing to do would be to verify it. And then finally, in describing sources of error for your experiment, do you think it would be more descriptive to list human error or improper measurement of plant height as a source of error? Well, we talked about this in the lecture part. You should never list human error as a source of error, because all errors are ultimately caused by humans in an experiment. So it would be better to write improper measurement of plant height. That was a source of error. Well, that's all for the review questions. Let's talk about a topic on science and Christians. And I was just going to talk a little bit about Francis Bacon. He's usually the man considered to be the founder of the scientific method. And I thought that would be interesting for you to know about him, since we're talking about the scientific method. And it's also important to know just about him. He was a Christian. He saw that God was orderly and organized in His creation, in His making of the creation and the things that are made. And so he wanted to have an organized method to study God's creation. Now look at what I have written there. It's easy to observe order and organization in our our universe, it's very obvious that there is order and organization. And we can use the scientific method to help us order and organize our work. That's what Francis Bacon did. And just try to remember and understand as you're doing science that God is orderly, organized, and purposeful. And so is the scientific method of reasoning. So by performing experiments that follow the scientific method, we can understand God better. Okay, well that's all for lesson 2.